These online resources are to help you get the best out of the How Science Works series. The first section gives a brief overview of the Key Stage 4 How Science Works programme of study. Later sections look at each of the 3 pupil programmes in depth, suggesting how these may be used as a teaching resource and illustrating some of the classroom activities which accompany these films.
Science isn't just about what we know, it's also about how we know it. So it's not just about remembering some facts. Now that's not to say that this huge body of knowledge that we've gathered isn't important. But what it does suggest is that it's also important to know something about where that knowledge came from. If young people don't know something about where this knowledge comes from, it's very hard for them to engage with science as they meet it on a day-to-day basis. Clearly, you can't engage with any scientific issue without knowing some science, some of the factual scientific knowledge behind it. But you need to understand where that information came from in order to make sense of it and to make decisions with it. The How Science Works curriculum can be seen as a tool for helping students develop their scientific literacy. So it's important for all citizens who are going to make scientific decisions, but it's also very crucial for our future scientists who need to know something about the scientific process and how they're going to go about further developing our scientific knowledge.
Each of our scientists has their own view of how science works, which may be quite different from that of the pupils. For example, Trevor Cox from the University of Salford.
I think when you look at the theories of how science works, it probably looks very structured, and it kind of, we have a theory, we make an experiment, we measure it, we prove it. Well, actually, in reality, science is much more messy than that. We might make some measurements and look at the data and think, oh, there's something interesting we've never looked at there, and then think, well, what does that mean? So you then have to have a theory. So you might go and chat to colleagues who might have worked in the area before and say, that means this. Or you might ring people up, or you might more often go and look in the literature and read round. So a lot of it is about happen chance, things you're kind of not expecting to find. It's probably as important in science as the things you set out to do. So you might set out to do something, but it's very rarely done in the same way. It's very rarely that you use the same techniques as you thought at the start. I mean, one of the funny things in research is you have to apply for money. You apply for 3 years' worth of money to do a research project, and you write this grand plan of what you do, and you write this plan, and first 3 months do this, next 3 months do that. And it never runs to the schedule, and it never runs exactly as you expect, because that's research. If it was all known exactly what you're going to do, it wouldn't be research, because research is about finding new things, it's about original thoughts, it's about original ideas. No one has trodden the ground before, so you don't kind of know what you're going to meet. It's a bit like the first person climbing Everest. You can guess what's going to happen, is they have to climb at high altitude and the effects of oxygen. But until you've actually done it, you don't actually know. And the techniques you might use to overcome that problem will depend on what you find when you get there.
The programme of study for How Science Works is broken up into 4 different areas: data, evidence, theories and explanations, practical and inquiry skills, communication skills, and applications and implications.
This strand of the programme of study explores how scientists collect and then interpret data and use it to develop new ideas and explanations. Data are pieces of information about an object or something that's happening. So, for example, Peter Styring measured how long it took several skiers to move down a slope. The data becomes evidence when you use that information to back up an argument or an explanation. So for Peter, he's using data about the skiers to back up his claim that self-lubricating skis are faster than traditional skis. What's very interesting is that 2 scientists can take the same data, and they may both agree that the data is valid and reliable, but interpret it in different ways. And Dr. Maggie Aderin talks about this in the context of climate change in her film. Clearly it's the way in which the scientists are looking at the data and their creative thought processes that are leading them in different directions.
The practical and inquiry skills part of the programme of study looks at the planning to test an idea, the collection of data, the analysis of data, and also how they evaluate. Evaluation is an area students are generally quite weak in, particularly looking at the validity and the reliability of their data.
For this section of the programme of study, students should plan to test a scientific idea, answer a scientific question, or solve a scientific problem. A range of approaches, including practical investigative work or researching evidence to develop an argument for a case study, provide students with opportunities to do this and to evaluate the validity and reliability of the data they draw together.
The communication skills strand of the new programme of study is not only about interpreting and analysing data, but also using that to produce an argument and then presenting that argument in the most appropriate way to another audience.
For this section of the programme of study, pupils improve their use of scientific language as they talk about their ideas and develop arguments. They also consider the use of both quantitative and qualitative methods to generate data, as discussed in Trevor Cox's film.
We can't ask people how do they feel about the sounds on the website, because with 1.5 million votes we wouldn't know how to analyse it. It's a big problem. So the website is very quantitative. We just get people to rate the sounds. We say just score this on a scale of effectively 1 to 6, because we can then deal with the data that we get.
The applications and implications aspects of the programme of study look at how contemporary science impacts on our daily lives, and also in terms of developments in science and technology, but not only in terms of the benefits, but also the drawbacks and risks.
The work of each of our scientists provides opportunity to discuss applications and implications of science. Maggie Adair's data affects the decision-making of government and society. Trevor Cox's acoustic models for concert halls and recording studios change the way we receive sound. And Peter Styring's team paid careful consideration to the impact of their lubricants on the natural environment. For this section of the programme of study, students should also appreciate that uncertainties in scientific knowledge and scientific ideas change over time, and the role of the scientific community in validating these changes. Maggie Adair and Trevor Cox both discuss how scientists share and debate their work, and how new ideas become generally accepted by the scientific community.
If we're going to address those different areas effectively, we need to use a range of different teaching and learning approaches. For example, problem solving, investigative work, data handling, and discussion-based learning techniques. Also, role play is very effective for dealing with the implications of science. To do this effectively, we need to choose the most appropriate technique for the area of how science works we want to engage the youngsters in.
For more details on how to use these 3 student programmes, go to the individual sections called Chasing the Wind in the Classroom, Bad Vibes in the Classroom, and Engineering Gold in the Classroom. You'll also find on this website the related CPD support and curriculum materials.